Okay, before today, I like to tell you something about all the classes that I have taken. Now you know what is a crystal, and we know how the crystal is being formed. What are the different types of crystals are there that you know? The crystals are being formed by the regular and systematic arrangement of the particles. Okay, so depending upon the type of arrangement they made, we can have 5 two-dimensional crystals and we can have 7 types of crystal systems. Again, we find when the crystal formation takes place, uh, it can be only present, particles can be only present at the coordinates of the geometric pattern, and we call them as simple or primitive unit cells. But in some cases, in addition to the particles at the corners, some particles are found deep inside the crystal body. We call them as body center crystals, and some of them may be present in the faces of the crystals. We call them as face center. And sometime with very few, we find the crystals are present in the alternative side, and we call them as end center. So if you take all this combination into concern, then we find altogether there are 14 types of crystals are there, and we call those crystals as brevis lattices. Okay, so this much we know. Then when you go for the crystal formation, then we have found, so there can be two-dimensional crystal lattice. The two-dimensional crystal lattice again can be of two types. One we find the pattern is square, and second one is hexagon. So we call them as two-dimensional square two-dimensional crystal lattice, and we call it hexagonal two-dimensional crystal lattice. The coordination number of square two-dimensional crystal lattice is 4. And in case of the hexagonal two-dimensional crystal lattice, the coordination number is 6. Then when we add the third dimension, again we find that if all the layers, you find the atoms are being just placed on the top of the another atom, and if the layering is same, we call it AA type. In that case, this leads to the formation of simple or primitive cubic unit cell. Then we can have another, that is the hexagonal pattern. Hexagonal pattern again can be of two types, where you find the second layer of the particles are being placed in the depression of the first layer, and that way if you go, you find that it forms a hexagonal close packing crystals with a coordination number of 12. And if you find that the second layer is different from the first layer, and in case of third layer, the particles of the third layer being placed in the top in the depression of the second layer. So you can have 3 different types of layers like A, B, and C, and that leads to the formation of the cubic close packing crystals. Again, here also we'll find the coordination number is 12. But ultimately we find whether it is a uh, hexagonal close packing or cubic close packing, you find both of them there result in the formation of face-centered cubic crystal. So in case of the body centered, sorry, in case of these simple and primitive unit cells, I have told you, I have shown you also that it has a coordination number of 6. In case of HCP and CCP leading to the formation of face-centered cubic crystals, the coordination number is 12. And we find is altogether different for body-centered cubic crystals, which is not being given in your book, but I have shown you also of the model. We find in case of body-centered cubic crystals, the coordination number is found to be 8. The atom at the center has 4 atoms from the bottom and 4 atoms above. So 4 plus 4, it becomes 8. Clear? Then we have gone for the packing efficiency. In packing efficiency, first of all, what did you find? We have found we established a relationship between the radius of the particle and the edge length. In case of simple and primitive unit cell, we have found the radius is half of the edge length. In case of the face-centered cubic crystals, we find the radius is equal to the edge length divided by 2√2. And in case of the body-centered cubic crystals, we find the radius r is equal to √3a divided by 4. Please remember these three because this is very important for your numericals. Now, on the basis of that, we have tried to find out or define the what is called the packing efficiency. Packing efficiency is nothing but that how much amount of the unit cell is being packed by the particles. That is how much is because I told you crystal is not like a can filled with water. There are a lot of empty spaces are there. The amount of space occupied by the particle is called, if you find it in the form of percentage, we call it packing efficiency. How do you find it? Packing efficiency is nothing but the volume occupied by the particles in the cubic unit cell divided by the volume of the cubic unit cells into 100. So therefore, when you calculated the packing efficiency of simple or primitive cubic unit cell, we have found it comes to 52%. In case of body-centered cubic crystals, we found it is 68%, and in case of the face-centered cubic crystals, which is most closely packed, it is around 74%. So rest of the portion which are free, now we call them as void. So immediately you can calculate the percentage of void by subtracting it from 100. So in case of the simple or primitive unit cell, it is 48% empty space is there or void is there. In case of body-centered cubic crystals, it is 50 to 48%. Not 48, it is 32%. And in case of the face-centered cubic crystals, it is 26%. Please remember, instead of asking packing efficiency in an exam, they may ask you the percentage of void. All right. Then we also try to find out the empty space or void which is there in the crystal. And we have taken our model as the face-centered cubic crystals. We found that there are two types of voids are there. One is called tetrahedral voids, other is called octahedral voids. And the octahedral voids are found to be located at the middle of each edges. A cube has 12 edges, so you'll have 12 octahedral voids at the center of each side, and one is deep inside the crystal, which is not being shared with others. So at every edge, we'll find 1/4 of the void is present because each side is being common to four unit cells. So in that case, you'll find only 1/4 of the void lies within one face-centered cubic unit cells. So if you want to find out the amount of the void we have, so in FCC crystals, it is nothing but 12 into 1/4 plus 1 is inside. So it comes to 3 plus 1 is equal to 4. And tetrahedral voids are not shared with others, and tetrahedral voids lie just below the corner of each cubic unit cells, and it is 100% inside. So total number of the tetrahedral void in a unit cell is 8. So now we know that an FCC contains 4 particles. We are talking about only of the unit cells, but unit cells are not visible to us. So several unit cells make a crystal lattice. So we know that each unit FCC unit cell consists of 4 unit cells, 4 particles, and it contains 4 number of octahedral voids, and it contains 8 number of tetrahedral voids. So you can find a correlation, that is we'll find it is in the ratio of 1:1:2. So if a FCC crystal means what? It can be made of CCP or HCP, but ultimately is FCC. So if a FCC crystal has n number of particles, you are going to have n number of octahedral voids, and you are going to have twice n number of tetrahedral voids. On the basis of that, we have already done around 3 problems to find out the molecular formula of the compound. These are not at all difficult. And after that, last class we have tried to derive also the density of a cubic unit cells. So we found the density of the cubic unit cells again depends upon the type of the unit cell you have taken, whether it is a simple or BCC or FCC. So we have got a formula, we call it nu rho is equal to m into z divided by n0 into a cube. So m is nothing but the atomic mass of the particle. Z is the number of the particles present. So in case of simple, it will be 1. In case of BCC, Z will be 2. And in case of FCC, it will be equal to 4. And N0 is nothing but Avogadro's number. And A is nothing but the H. Okay. So this we talked about an ideal crystal. But everything which is found around us, or we try to make it, we cannot make as per the theory. Okay, some deviations are always there, and this is, we call it defect or imperfection. So today you are going to discuss about crystal defects or imperfections. Okay, so right now here, imperfections or defects in solid. See, we know crystals are formed by the regular arrangement of the particles. Okay, so say this is the one. I'm only drawing the front side. See. So if in all the places the particles are there, then it will be ideal crystals. But we find ideal crystals are only possible only at 0 Kelvin. Please remember, it is not okay. 0 Kelvin. As the temperature goes higher and higher, because we know even to 0 degrees Celsius we equal to 273. So 273 Kelvin or 0 degrees Celsius is a large difference from or deviation from 0 K. And what we consider room temperature, all scientific study we do at room temperature. Room temperature is 25 degrees Celsius or 298 Kelvin. In such cases, we find many of the particles which are supposed to be present in the crystal, they go missing. Either they leave the crystal or they move to a new location. So this type of movement or disappearance of the particles from the main crystal is known as imperfection or crystal defect. See, in your classroom, suppose you have 25 benches and each bench 2 of you are supposed to sit. Some days it may happen all of you are present and all of you are generally in classroom. We find that every student generally they prefer to sit in a place of their liking, and once they start sitting they do not change that seat. Okay, so if these are the students sitting in their respective to each, it may happen. So it's supposed to be all of you are supposed to be present every day in the class, but it may happen that due to some sickness or some other reason, maybe that the 2 of them could not come. So these places are vacant. So this is not a order. Or maybe that they came, but as they are talking too much in the class, the teacher told you go and stand outside. In this case also you find some places vacant. So this leads to disturbance in their arrangement, and that we call it crystal defect or imperfection. Okay, so this is so similar to us. All right. So let me write down. Let me write down this definition. These definitions are there in your book, but still, let me write down. Any departure from the properly ordered arrangement in a crystal is termed as imperfection or defect in a crystal. This when we'll discuss everything. Now we can classify this imperfection in two categories. I'll go very slowly. If you don't understand immediately, tell me. And if that small thing which I give you, please write down. If possible, I'll give you the note. If not, then forget. The imperfections present are mainly of two types. Two types are there. Electronic imperfections, or you also call it electronic and second one we call it atomic imperfections or atomic defects. To explain to you, these are very easy. So even after that, if you don't understand, please tell. So let us go for this. So we'll go for electronic imperfection or electronic defect. See, what is our ideal model? Ideal mode is 0 Kelvin, where you find atoms are, all of them are rightly placed. And the electron inside the atom or electron present in the bond are also in the right place. Okay, so let me take a solid like this. Say it is silicon. Silicon, so you know. What is the valency of silicon? Remember? Hello? What is the valency of silicon? Who is going to answer? Open your mouth. I told you no. If you feel shy, you can never learn in your life. Never. There are thousands of things which I also don't know. Yeah. What is the valency of silicon? Silicon, yes, correct. Silicon is in which group? Which group? Yeah.
14.
Good boy. See, initially the crystal, did you not see? I forgot. Then someone reminded me, sir, you did not discuss about the covalent and network solid. It was a boy only. Who was he? Tell me the name. I cannot remember your name. Who told me? Sir, you did not discuss covalent and network solids. Huh?
Malem, sir.
Yes. So see here. So I have taken silicon. So all the silicon are covalently bonded to each other. So I told you that when I teach you, please keep your book open. It may happen that I may forget. So, and if you feel shy that how to tell sir, then so you will be cheated. I will not. Or maybe that I want to avoid also teaching this one. So immediately you can catch me. So sir, why you did not teach this one? You should be like this. In school also you are not saying anything because of that many teachers they teach you half and they don't teach you the other half. See, this is silicon. See, this is the covalently and network solids. We know covalent molecules are not ionic, so they do not conduct electricity. See, salt, if you melt it, it conducts electricity. Iron, copper, they conduct electricity because they are metals. But a non-metal, they don't conduct electricity. Why? Because in between non-metals, you have covalent bond. So silicon, silicon is a non-metal. So any substance which does not conduct electricity, what do you call them? What do you call
What?
a substance?
This
Huh? Yes, yes.
insulated.
Yes, we call it insulator. Please remember, silicon is an insulator. Carbon is an insulator. Below carbon, you have silicon. Below silicon, you have germanium. These are all insulators at low temperature. Carbon is insulator even at high temperature. Exception is there, we find in case of graphite. That is a separate story. Okay, see here. But this up to class 11, these days you people know much more than us because we did not study all this thing, whatever you are studying. You know, silicon and germanium are used as semiconductors. This we are again going to study. And in physics, you will study a whole unit is there on semiconductor. What is semiconductor? Semiconductor is a substance which conducts electricity when you heat it. Otherwise, at room temperature, it is an insulator. So let us try to see. See, this is a perfectly ordered arrangement of the crystal. So there are not supposed to be any defect because all the silicon are bonded to each other through covalent. Clear? All right. Now, when you heat it, moment you supply heat, you know we have studied in atomic structure, electrons remain in their respective orbitals. But if it gains any energy from the external source, then the electron absorb that energy and undergo electronic excitations. That is from lower energy level, it goes to the higher energy level. This is the arrangement of the silicon I have done, that is at 0 Kelvin. But think of room temperature, 278, 98 Kelvin, or say 300 Kelvin. A large difference of temperature is there. In this case, what is going to happen? We know that also you have learned in class 11, bond dissociation enthalpy. What is bond dissociation enthalpy? It is the amount of energy, generally we say in the heat only, required to break a 1 mole of bond. Where from the energy comes? From heat. So when you move from 0 Kelvin to 300 Kelvin, 300-degree difference in temperature is a huge temperature. What happens here? In this case, you will find the bonds are broken. Say this bond. See, in covalent bond here, perfectly covalent bond, it always undergoes homolytic cleavage. Remember I told you homolytic cleavage? So what has happened now? In this case, in this bond, one electron belongs to this silicon and other electron belongs to this silicon. So when they break, what happens? So this is the orbit. You are having one electron here, and you are having one electron. The bond is broken. Also, you have learned in atomic structure, what is the maximum number of bond one orbital can have? Tell me. What is the maximum number of bond an orbital can have? Each, not orbital. Each orbital can have how many electrons? Tell.
8.
Huh? Each orbital can accommodate how many electrons?
8.
2 and 8.
2.
No, I have told you at the very beginning. I am not talking about orbit. I am talking about orbital.
Sir,
What?
2.
Yes. See, orbit is 1, 2, 3, 4. KLMN. Orbital is S, PX, PY, PZ. Okay, so each of them can accommodate 2 electrons. So what will happen? See, this is orbital. So this electron from here, it can go here. Huh? See here. It can go here. Okay. This electron from here, it has gone here. What has happened now? This place has become empty or not? This place has become empty. Then what is going to happen? After some time, you may find this bond may break. If this bond breaks, both the electron will go here. This bond will break. Now these 2 electron will go here. What will happen now? Electron has come here. Now, say this bond is broken. Say this bond is broken. Then this electron can go here. So what is happening? See here, electrons are moving in these directions. See, when the electrons are going in this direction, what is going to happen? See here, you will find empty places there. So these empty places are called holes. These empty places are called holes. Which way the hole is moving? In this direction. Which way the electron is moving? In opposite directions. Okay. So ultimately, what is going to happen? You will find it is going to conduct electricity. What type of defect it has created? It is electronic defect. How it is being created? How this defect is being created? The defect is being created by heating it. So this type of defect is called electronic defect or thermodynamic defect. Once you cool it, you will find. Okay, now see here. Before I'll talk you, I'll tell you later. Now see, when this type of holes are being created, suppose it is a wire made of silicon. Okay, made of silicon. Now this is whatever I have shown you is the magnified portion of the same wire. If this wire is being connected to an electric plug, what will happen? From electrical plug, electron will come or not. So this electron will come here. Then it will travel through all the hole and go to the other side. Okay. Now you understood that why this type of species conduct electricity. This type of species conduct electricity only because of the electronic effect. Okay. Now you stop heating and remove it from the plug. You'll find again it has become whole part. All right. So this type of defect is called electronic defect or thermodynamic defect. Why do you call it thermodynamic defect? Because this type of defect arises only when you heat it. Otherwise, at room temperature, otherwise at normal at 0 Kelvin, they are not going to conduct electricity. They are perfectly all right. Only on heating only the electron starts moving. So these type of defects are called electronic defect. Many times this question comes. Why silicon is an insulator at room temperature? All of us, you know, silicon is semiconductor. In the exam, when you went, you have found question is just different. You read about semiconductivity or movement of electricity, there is found is electron. So what you will write? You will write under normal condition, the silicon bond does not break. Hence, they do not conduct any electricity. So it is an insulator. Now, in that case, why why diamond does not conduct electricity? Because carbon, silicon, germanium, all of them are found to be covalent on network solids. Why they do not conduct electricity? Simple reason. Carbon is a small atom. Carbon-carbon bond length is also very small. So it is very difficult to break the carbon-carbon bond. Hence, they will not conduct electricity like silicon and germanium. So this is the story of electronic defect. What did you learn from there? We have learned when you hit this type of covalent and network solids, the covalent bond between the atoms they break and set free the electrons and also generates empty orbitals or holes. These electrons move in one direction and the holes move in the opposite direction, and hence they conduct electricity. Such type of defect is called electronic or thermodynamic defect. Now we'll go for second one. That is the atomic imperfection. One thing, last year I have, when I taught initially with the online classes, I have given them some notes. So I can also give you the notes of the chapter that I have written here, but my notes are much bigger than your books. because I have discussed there elaborately everything which is missing in your book. So if you wish, you tell me, otherwise not. But it will going to take some time because I have to make them their PDF. Some of the 5 chapters I did not make PDF files. So if you wish, you tell me, or you can post me in the group, but it will be long. Second one. Atomic imperfections or defects. So let me write first definition. The defects which arise due to the irregularity in the element of constituent particles. If you know physical particles, means what? It can be atoms, molecules, or in a crystal are called atomic defect or imperfection. Please write. I told you not after finishing, you tell me.
Done, sir.
So I'll go for now. Point. See, the places where the constituent particles are present in a crystal are called points. We call it lattice points. Okay, like in simple and primitive unit cell, how many lattice points are there? 8 lattice points are there. 4 at the top corner, 4 at the bottom corner. In case of BCC, there are 5 lattice points at there. 9 are there. 8 at the corners, 1 at the inside. And in FCC, there are 14 lattice points are there. 8 at the corners, 6 at the middle of the each faces. So please remember. That is, if some of the particles do not reach there, or if it is there, it has gone up.
Done, sir.
Okay. So let us go for this one. Say, in a classroom, to maintain the sex ratio, we have 10 boys and 10 girls. Okay, so what is the ratio? 1:1. Due to some reason, one boy and one girl are absent. See, their place is vacant. So it is a defect. But what is the ratio of the girl now and boy? Is 9:9, means 1:1. So this type of defect is called stoichiometric effect. Particles are missing, but the ratios are not changed. So the formula will remain same. Okay. Say in a unit cell of sodium chloride, we have 4 sodium ion. At the 4 sodium ions are present in the voids, octahedral voids. Okay, and we have 4 chloride ions, which is forming the crystal, lattice voids. Due to some reason, if the one of the sodium ion goes, then its ratio will be Na3 plus and Cl4 minus. So in that case, what will happen? The sodium chloride crystal will have a negative charge. All salts are electrically neutral. See, when you take little bit of salt, you never get a shock. Because if the electrical imbalances are there, then you obviously will get a shock. If you touch a live wire, you get a shock. Why? In live wire, only electrons are flowing, protons are not flowing. So because of that, you get a shock. But the same wire, electrical wire, if you switch it off and touch with your hand, you will find you'll never get a shock. Because the metal wire, in the metal where metal atoms are there, they're having same number of electrons and protons. So all salts are electrically neutral. So when this type of defect occurs in a salt, in that case, what will happen? If one of the sodium ion goes out, chloride ion, even if it is not interested, he has to go. Why? Because In that case, the salt will be again electrically neutral. So by that way, the formula or the ratio of these cations and anions are always same. So let us write now the definition of stoichiometry.
Done, sir.
Okay. So now we'll see. See, normally, how can you have a point? Huh? How can point defect you guess? See, you are my teacher. We always think of idea. Nah? Okay, see here. These are the places you sit. So you are present. Don't write. Huh? See here. So how many are absent?
2.
2 are absent. How do you know they're absent? How do you know they're absent?
Because it is not written
Huh?
as present. Because it is not written as present.
No, no. That's the I have written. Even the teachers does not take the roll call. Student knows that some of your classmates are missing. How do you know that their classmates are missing? So this as a teacher I have written. So you also know. Before teacher knows, you know that some of them did not come. How do you know that did not come?
Because the places are empty.
Yes. These places are empty or okay. So this defect is known as vacancy defect. These are called vacancy defect. Okay. That is some places are empty. I see here I have not taken any ions. I have taken a molecular crystals. Molecules do not carry any charge. Okay. So these are called vacancy. Okay. That is some of the places are empty. So they are vacant. So we call them vacancy defect. So what will be the consequences of vacancy defect? What will be the consequence? Tell. Okay. Suppose a crystal is supposed to have big crystal, I'm saying, not units. A brick, a ideal or perfect crystal, suppose you have made, and you now you know how you can calculate how many atoms are there or how many molecules. I'm taking a molecular crystals. There. You know by this time you know their molecular masses. As the crystal is big, with the help of your scale also you can measure its edge length. Okay. So now you know that what should be the mass of the crystal. That is, a crystal is having 1000. Say you have taken a crystal of urea. Urea molecular mass is 60 gram mole inverse. Okay. It contains say 1000 urea molecules. So you know that what is the mass of one urea molecule. You know it very well. Is 60 gram is the molecular mass. What is the mass of one molecule of urea? 60 divided by Avogadro's number. This is the mass of 1. And for 1000, again you will multiply it by 1000. So you should know that this is the weight of this crystal. But when you taken the weight, you found it is less. Why? Because some molecules of urea were absent. They did not turn up. Just like in a class of say 64, say you are supposed to sit by 8 by 8 column. In that case, you found that 4 of them did not come. So if someone take the total mass of your class, you will find it will be less. All right. So what will be the consequences? When the mass decreases, you see crystal shape did not change. Mass has decreased. So what is going to happen? Mass by volume is what? What do you call it? Mass by volume?
Density.
Yes. Consequences of vacancy defect, that density of the crystal decrease. Take care. Vacancy defect always lowers the density of the crystal.
Excuse me, sir. You
Yes.
have written consequency instead of consequences.
Oh, yeah. Good, good. Consequences. Consequences. Thank you. Consequences of vacancy defect is density of the crystal decreases. Okay, so this is one type of. Okay. See now. Now the most of you are having your car. But maybe a few years back, when you were very small, you may find that maybe that your parent was not having a car, so you used to travel by taxi. So when you went along with your parents, then you'll find your father or mother has paid for two. Mother and the father. As because we are very small, you also went along with them. For that, a small place is being created for you in the taxi, and they did not pay. Even the taxi driver also did not pay. Okay, so it may happen that when the crystal formation has taken place, and if the molecules are small, okay, so what will happen? See, the empty spaces are there now. The empty spaces are called the void or interstitial spaces. So you may find that some of the molecules have occupied just because they are small in this interstitial spaces. Okay. Whatever the number of the particles supposed to be present, all of them are present in the right places. But along with them, 1, 2, or 3 will come extra and occupy those interstitial spaces or vacant spaces. So this is also a defect because they are not supposed to be there. Okay. So this type of defects are called interstitial defects. These are called interstitial. These are the interstitial. So these are called interstitial. Interstitials. Okay, or interstitial spaces. Okay, or also known as voids. So you are going to have interstitials effect. Okay. So now, can you tell me what will be the consequences of interstitial defect? What will be the consequences? So, what is the consequence?
Sir, density increases.
Yes, because extra are there now, the weight has increased. So in that case, you find density. So we can write now. Both vacancy and interstitial defects are found in molecular or metallic crystals. Done. So now we'll see we'll go for ionic crystals. These are very simple. Defects in ionic crystals. First of all, you should remember all salts or ionic compounds are electrically neutral. Okay, so let me go for one crystal of sodium chloride. I'll wrap this portion. First, you try to understand. In my class, if you don't understand, I'm going to repeat it 10 times. But if you sit like a monk and pretending that you have understood, I have no sympathy for you. See here. So I'm not writing any ion. Okay, I'll write Na plus Cl minus. Na plus Cl. Na plus, then because oppositely charged ion will always remain that. Na plus Cl. Na plus Cl. Na plus So this is an ideal crystal of sodium chloride. Ideal crystal. But it may happen one of the lazy fellow sodium he did not come. Moment sodium does not come, see this whole crystal will be having excess negative charge. What happened? Whether it wants or not, any chloride has to go. It's not that it's nearby chloride has to go. It may also. Okay. So because to maintain electrical neutrality, a chloride will go. That is, as many number of sodium ion go, same number of chloride also will go. Okay. So this type of defect is nothing but a this type of defect is nothing but a vacancy defect. But when the vacancy defect occurs in an ionic crystal, we give some other name to it. So when vacancy defect occurs in an ionic crystal, it is known as I call it Schottky, some say Schottky. So up to you. We call it Schottky. So in that case, you'll find now it becomes electrically neutral. See, suppose this sodium has gone out. It may happen, this chloride may. Okay, so let me remove this one. So I'll remove this one. Write this one, then we'll write something more.
Done, sir.
Okay, now what type of salts is going to show you Schottky defect? We'll write now. Schottky defect occurs with those type of ionic solids where both cations and anions are large. Example, alkali metal halides with higher coordination numbers. Okay. Now, what is the consequence? Consequences in your book only one has been given. I do not, somehow I do not agree. Huh? Why? Because you have to appear intrinsic. Okay. See, first of all, number of the cations and anions has decreased is density will be less. So what is one? Lowering of density of the crystal. That is obvious. As you know, because it is a vacancy defect only. Then what will be the second one? See, these places has become empty. As these places has become empty, now can you call it is a closed packing? Suppose from your suitcase you have first you packed it with a lot of clothes. Then after some time your mother has come and removed 10 of them from there. Useless. These are all dirty. Why you are taking? In that case, what is going to happen? The packing inside your suitcase will be loose. It will be soft. All right. So in that case, what will happen? Moment you heat it, the crystals will ions will start moving. So what will be this one? Lattice enthalpy and their stability of the crystal decreases. Now it becomes soft. And these particles can move now. Vacant spaces are there. What is the third one? Entropy increases.
Done, sir.
Finished. I'll do one more after that. If I don't do the other one, then also it won't be complete. Finished.
Yes, sir.
So,
Yes, sir.
So now we'll go for another types of crystal. That you call it Frankel. See, in this case, you'll find both the cations and anions are smaller. And generally, cations are smaller than the anions. This type of defects arise when the side of the cations are smaller than anions, and they leave their position. Moment they leave their position, what is going to happen? Vacancy defect. And occupies the interstitial see. So what does it create? It creates a interstitial defect. Okay. That is, they leave their own place and come to the among the other anions. So they create two types of defects: vacancy defect and interstitial defect. But none of the particles they leave their lattice. They remain within. This type of defect is also known as dislocation defect. Dislocation you know very well. Why? Suppose you fell down badly, then you see you are not able to move your feet. You went to hospital, doctor has taken the X-ray. He told you no, the bone there is no fracture. But only thing is that the joints have displaced. So what he calls? He calls his joint is being dislocated. Dislocation has taken place. Okay. So this is called Frankel. See here. Cation and cation and then see here. Cation has come here. This place become now empty. See this. So what is this? This is vacancy defect. And what is this? This is interstitial. So this is called the Frankel. Right.
Done, sir.
Okay. Now, what type of substances is going to show? I told you what is the condition. Cation should be smaller than anions. So, example. So, we know in the periodic table when you move from left to right, what happens? The size of the cation decreases. Huh? So, what type of substances will show this one? It will be shown by silver chloride, silver bromide, silver iodide, zinc sulfide, etc. So, what is the consequences of Frankel defect? See here, none of the particle has left the crystal, so weight will never change. Consequences of Frankel defect. What is one? It does not lower the density of crystal. Why? Because none of the particles have left the lattice. Second, see here, two positive charges are very close to each other. So it leads to repulsion. Means in that case, the crystal, see, it is fact that number of positive and negative charges are same, but in each row you see, there should be uniformity in the charge. In this case, because of repulsion, the charge is being disturbed. And this type of effect is called dielectric property. Second, it increases the dielectric property of the crystal due to the closeness of similar charges. This phrase has become empty, so this will make the packing loose. So what will say? Thermal stability of the crystal. Then fourth what? Entropy. In your book only this is given. You should know for your entropy.
Done, sir.
Now open a question task. That's one more thing I have to write. What is the exception? The exception is silver bromide shows both Schottky and Frankel defect. This is very important for your exam. Now, one question is often being asked. Why do alkali metal halides do not exhibit Frankel defect? See, what is the condition? Condition is that size of the cation should be smaller, but alkali metal sizes are ions are bigger. So what should you write now? Alkali metal cations have larger sizes and cannot be accommodated in small interstitial spaces. So they do not show Frankel. Thank you.
Done, sir.
Okay then. Bye for today. If you have any question, please read the textbook. And if you have any question, next Tuesday ask me. Huh? If you want to learn at a time, read this portion that I have taught you. Ask me. No problem.
Bye, sir.
Bye.
Thank you, sir.
Thank
Okay.
you, sir. Thank you,
Welcome.
sir.
Mark present.
Bye, sir.